Okay, so I think we can start. Today, we are having Eliad Tsfadia. He's a Ph.D. student at Tel-Aviv University, and his advisor is Edith Cohen. He's also an intern at Google Research Israel, working with Edith Cohen, Haim Kaplan, in Yishay Mansour, and Uri Stemmer. He has a lot of paper and some projects on differential privacy that we're very eager to hear about. He is going to talk today about tools for differential private aggregation. So without further ado, I will let Eliad to start. Thank you.
Thank you very much. So I'm Eliad, and this talk is based on a joint work with Edith Cohen, Haim Kaplan, Yishay Mansour, and Uri Stemmer about FriendlyCore, a tool for differentially private aggregation. So before getting into the details, I will spend one slide to introduce myself. So as we said, as Mariam said, I'm a PhD student at Tel Aviv and a researcher at Google. So I have works in Tel Aviv on cryptographic protocols, and at Google I have works on the differentially private algorithms. I also have one work that in the interconnection between cryptography and differential privacy. And this talk is actually about this part of my research. It's about a tool, a generic tool for averaging and clustering, and hopefully for other applications. So let's start with a quick recap about differential privacy. So in this talk, a database D and D prime are neighboring if the symmetric difference between them is 1, which means one database contains the other plus an additional point. And we said that an algorithm A is differentially private if its output on neighboring databases almost indistinguishable. And by that, it hides the presence of any single point. And usually this indistinguishability loss is captured by an epsilon delta parameter. So we say that A is epsilon delta DP. If for every neighboring D and D prime and any event T, the probability that AD is in T is epsilon delta close to the probability that AD prime is in T. And in this talk, we are also considering the different model of zero concentrated differential privacy, or in short, zCDP, which has a parameter rho. So A is rho zCDP if for every neighboring D and D prime and any alpha larger than 1, the Rényi divergence of order alpha between AD and AD prime is at most rho alpha. And this definition can also be extended to what we call approximate ZDP, zCDP, with the delta parameter, like in the differential private, that basically capture the probability of a small probability of a bad event that might happen. So let's start with a quick example of basically the Gaussian mechanism for DP averaging. So the setting is that we have points in RD, and we would like to estimate the average. So usually we need some bound on the diameter of the points, some large lambda. And then what we are doing is that since the average has sensitivity of lambda over n, so we are adding a Gaussian noise with sigma that is proportional to this big lambda. But sometimes sometimes we have cases that this lambda is very large, but D might have a much smaller effective diameter R, and we wish to replace this big lambda with R in this sigma to gain in the accuracy. So for example, for this friendly, what we call friendly database, all the points are actually in this diameter R. So we really want to just add noise to proportional to this R. But this is hard with differential privacy because DP is a worst case guarantee. We really need to handle also cases where there is a point here this is an almost friendly database, but the outputs on these two databases should be similar. So, so the wish for our what we call FriendlyCore paradigm is to construct something what we call a friendly DP algorithm A, which is a weaker notion of privacy. It's only DP only when the input is friendly. Okay. When we don't have outliers, everything is okay. But when there are outliers, we might not guarantee a DP at all. But with this weaker notion of privacy, we can do accurate and simpler solution than the unrestricted counterpart. And the idea is that we will have the tool FriendlyCore. It will get a database D, might contain outliers, but it will just output some core C, subset of this D, and this core will be certified to be friendly. Okay. And then when we have this guarantee, we just apply A on this core C. So let's see an example. So in this case, this D, most of the points are with diameter R, but there are some outliers. So we hope that when we wish that when we apply this FriendlyCore, it will give us, it will remove the red points, it will give us the core C here. And then we just add noise proportional to this R. So in this example, a friendly database C, it means has diameter R. This is a friendly, without this point, this is a friendly database. And a friendly DP algorithm A is an algorithm that just add noise that proportional to R. Okay, this is not a DP algorithm in general, but when the database is guaranteed to be friendly, it is okay. So let's see another example of the sample and aggregate framework. So basically the idea is that in many cases, a random sample of the data provides a good answer non-privately. So the idea is that we have some problems. So we have some database, we randomly partition it into n equal parts. And then in each part, we apply some non-private algorithm. Each such execution gives us a solution yi, which should be good. And the solution we hope to be similar. And then we need to do some private aggregation of all these solutions in order to get a private y and return it. So we expect that the solution to be mostly similar, but this is just for utility. For privacy, again, we cannot, we need to handle also cases where the YRs are not similar. But if we are guaranteed that if we are guaranteed that the YRs are similar, that there are no YIs, there are different like outliers, then this private aggregation can be simplified. Okay, so basically the idea is that we take all this YI, we apply FriendlyCore, and then we can use a much simpler aggregation algorithm in this case. So for a concrete example, let's see clustering. So here we have a database of points in RD and the parameter K. And basically we randomly split D into n subset, and we execute some non-private algorithm in each subset. So each such execution gives us K centers, in this case 3. So we have these red centers, the pink, the green, the yellow, the purple. And then when we are done, basically we have a different problem, which we call a k-tuple clustering. So now the input is a database of unordered tuples over RD or k-tuples, with the utility promise that the tuples are partitioned by far balls, which means that there exists some far balls that each ball contains 1 point from each tuple. And basically the goal of this task is to privately identify a new k-tuple that is close to them. For example, this yellow tuple here. So let's see, for example, an example. So what is a friendly tuples? So if you look at this example, This is not friendly because of this pink tuple, which is not in the structure of the other tuples. But if we remove this pink tuple, then we are getting a friendly database. Okay. So what can we do with that? So again, so a friendly database C is the tuples that are partitioned by farballs. And what will be the friendly DP algorithm A in this case, as when we are guaranteed that the tuples are indeed in this structure, it will be just pick an arbitrary tuple, for example, the red one, which let's say it's the first one. And then we just split the points into k sets according to this tuple, okay? Actually, we get the right clusters, and then we probably average each such set. And okay, to get the averages. So the key part here is that this step 2, splitting the points into k sets, is not trivial. Okay. Because we use a tuple which is sensitive. This is like the individual data, okay, in order to split the points. But still, when we are guaranteeing that these tuples are indeed partitioned by farballs, it doesn't matter which tuple we take. This is the index. We don't have outliers. So this is like.
Eliad, can I ask a question? I'm actually confused by I think I lost track of types, maybe. What does it mean when you say pick an arbitrary tuple, that's like a k tuple? Like an arbitrary point?
Yes, just a second. Pick an arbitrary, so the database is so each element in the database is a k tuple, like all these rand points are one tuple in the database. All these blue points are the second tuple in the database, okay?
Actually, maybe I misunderstood what the input is here.
Okay, so let's go back one slide. The idea is that all the tuples, so we started with points, okay? We started with points, and then we apply a non-private algorithm, a k-means, let's say k-means algorithm. Each such executions give us k-centers, okay? And now we are treating to each such a solution k-center as a single element in the new database, okay? One of them, sorry?
I see. So you're thinking of the data set now as a list of these k-tuples.
Yes.
Right?
Yes.
Yeah. So I got mixed up between the two data sets in the notation.
Yes. So now like there is a different problem of k-tuples that unordered. So maybe in the first execution, this will be the first center and this will be the second, but in the second execution, it might be different. Okay, but I know that they have structure, like there is one center here, one center here, and one center here. Okay, this is why I call it unordered tuples. Okay, they are, I don't know what is the order of, I don't know that the first point of each chart you see. I don't know that, but I know that they have such a structure. So I treat them as just the red points are the unordered tuple. Okay.
I see. So, and are you, maybe you formalized it and I just forgot, but what by far balls here means there's like a separation guarantee between the.
Let's say that the radius of the ball is much smaller than the distance from other center of the other balls. Okay, for each
much
ball,
smaller is like a factor of 3 or a factor
of let's say 3. Let's say 10 for now. Okay, let's 10 or something, some constant, large enough constant.
And you have a guarantee that this is going to be the case, that the points can be partitioned this way, clustered.
Okay, so I'm going. I don't know if I have a guarantee. I can hope that I will have this guarantee. In some cases, there is such a guarantee. Okay, but I can verify it. Like I can try to see whether this is the case. If this is not the case, I will output an empty core or something like that. Otherwise, I will get a core and a friendly core which contains such tuples. Okay, So there are cases in k-means, for example, when you assume some common separation assumption that you are really guaranteed to have such a separation. Okay, but sometimes it's in some cases it can be without a proof, but this is okay. Okay, we will see about it. Okay, for now I'm just saying that for utility I'm hoping that this will be the case. Okay, for utility, and if this will be the case, then I am fine. Okay, I'm going to verify that this is the case. If this is the case, I will give a nice score and everything will go through. Okay. So now I didn't prove
forward to the sensitivity analysis.
Sorry?
I said I'm looking forward to the sensitivity analysis.
Yes. So I will. Okay, I will complete the picture in the next slide. Okay. For now, let's. I don't prove that this is going to happen. Okay. The utility, there is a utility part here that the tuples should be far by 10 times. Okay, but this I'm saying what I'm saying that even if it doesn't happen, this is not going to hurt my privacy. Okay, this is if it's happened, then great. If it doesn't happen, I'm just going to fail or something like that. Okay, this is like for the framework. Okay, I'm just saying that I'm expecting that this will happen and I'm going to check it. Okay, but if it won't happen, then okay, so I'm going to, so let's complete the picture in the next slide. Okay, so for now it's just for the intuition. Let's suppose that I'm expecting it to happen, and then what I'm going to say, what I'm just saying that if I have a database, this is really the structure of the database. This is just what I'm saying. I'm defining a friendly database. If this is the case, then the clustering is trivial. Okay, this is just what I'm saying. I didn't say how do I get this database, but this is like the intuition for now. Okay. So I just want to point out again this algorithm here again is really not private, not standard private. So let's see an example. Okay, if we're looking, for example, on this is the algorithm, and let's suppose that this are the two databases. We have D and D prime, and D also has this tuple, the pink tuple here. So if we just follow this algorithm, pick the first tuple, and then so let's pick the first tuple, and let's split the points into k sets, and then just average each set, then we will completely get different results, because again, it's step 2. The splitting will be completely different. So when D is not friendly, step 2 may induce different clusters. Okay. Yeah.
Sorry, at least on our projector, the colors don't come through entirely clearly. Can you just go? So I think what you're saying is you're going to pick the a tuple that you might get unlucky and pick the pink tuple, right? And then when you say split the points, so you're going to for each other tuple, you're going to find like what, a min weight matching with the first tuple. And like, what does it mean to split the points according?
Split the point, just ignore so now ignore the colors of just treat it as a set of a lot of points, and each point will be close to the nearest point in the tuple that you chose. Okay, so it's like in case you have case centers that each point belongs to its nearest center.
I see, but they're not necessarily like case sets of the same size.
They're not necessarily no, yes, no. So if okay, for now, yes, this is not necessarily, maybe it will not be, but in case that what I'm saying is that if this is not friendly, you can get completely different clusters, you are losing control. But when D and D prime are friendly, okay, there are no such outliers, like you started with tuples that really partitioned by far balls, then it cannot happen. Every tuple that you will choose will induce the same clusters, and it will be equal size clusters, okay?
I see.
It will be like the picture, I don't know if you see, like the picture here. It cannot be differently. Again, but you need somehow to remove the outliers. Like in the averaging case, you had outliers and you want to remove them. Here, the outliers are the bad tuples. Okay, this is like the intuition.
Right.
Okay, is it clear?
I have a question. Sorry, a quick question. So in the first picture, you say that you mentioned that when you're splitting the points into k sets, it's possible that each of the k sets may not have different points, but like, how is that the case? Like, isn't each of the case set supposed to have like m points or something?
So if we started with, again, I started with k tuples, like in the picture here. So I started with this is like the case. I started with k tuples that really partitioned by far balls, like this, this, and this. Okay, and in this case, what I'm saying that if you take an arbitrary tuple, then it will induce a k cluster, equal size cluster, exactly the clusters that you want. Okay, it cannot be differently. There are no empty cluster or different size cluster in this case. This is like in case that really the database is such friendly. Okay, this is what I'm saying. If the database is guaranteed to be such a friendly database, it must happen.
Sure, but like I was asking, like for the first data set, like for D, like that's not necessarily guaranteed. Like even if
no, if it's not necessarily, maybe one of the cluster is empty even.
Okay.
It can be, yes, it can be empty. It can be you're losing. This is a completely bad algorithm.
I see. Okay, cool. Thank you.
Okay, what I'm saying that if I somehow guarantee that the tuples are really friendly, then clustering becomes trivial. This is all what I'm saying. Okay, so now we're going to see how it's going to happen. So this is basically the algorithm FriendlyCore. Okay, it's also holds for averaging, clustering, and other problems. So we have some database D from some domain X, and we have a predicate of whether of 2 points, whether they are friends or not. And for each element X, we count the number of its friends. Okay, the number of Y's such that fxy is 1. And then what we are doing with probability Q of discount, Q of C, we are adding this element to the core. So what is this function Q of C? So what we want is that if this element, the count is nth, it means it likes all the other elements, like for example, in averaging, it's close to them in the distance R, then it will be in the core with probability 1. If it likes no more than n over 2, then I'm going to remove it from the core. And otherwise, I'm going to use some smooth probabilities that such that Q of C is similar to Q of C plus 1. And the idea is that, so let's see what's happening in averaging. So in averaging, the domain is RD, and we have some parameter R, what we are thinking that this is the effective diameter. And the predicate is just fxy is 1 if the L2 norm is smaller than R. Okay, this is for averaging. And for k-tuple clustering, the domain now is k-tuples over of points in RD, unordered tuples. And tuple T likes tuple T prime. If for every point in T, there is a point in T prime, such that the distance between them is much smaller than the distance from X to the other point in Y. It means that there is one-to-one mapping between the T and T prime. Okay, so for example, in this case, so X and Y here are the red and green are friends because there is a mapping between X1 and Y2, X2 and Y3, and X3 and Y1. Okay?
Eliad, is T prime the same thing as capital Y?
Is T prime, again, what is the question?
In your minimization, you've got a capital Y.
Oh, yes, yes, this is T prime. Yes, sorry, this is T prime. Yes, this is the type. Thank you. This is T prime here. Yes.
So there's essentially like a very clear matching between.
Yes.
That's
Yes.
the condition that you're working on.
Yes, exactly. So what is the utility of this framework? So going back to the general tool. So if all the points like each other, then basically I'm going to output, the core will be all deep, okay? And for privacy or some step for proving privacy, so if we start with neighboring databases, so basically because we are using such smooth queues, what we are getting that up to the additional point, the cores should be similar. This is the intuition. And also, this is the very important property, the union of the two cores is certified to be F-friendly, okay? And what is F-friendly? Let's now define it formally. So a database S is F-friendly if for every point xy, there is a point z such that x is a friend of z and y is a friend of this z, okay? And why we are getting this kind of guarantee is because if you're thinking about what get inside the core, it's just element that has at least it's more than n/2 friends. So if you look at the friends of x and the friends of y, there must be a z in the intersection, okay? So basically we are guarantee that we are guarantee some similarity. We don't guarantee that x is a friend of y, but we are guaranteed that x is a friend of, like x is similar to z and y is similar to z, so in some sense x is similar to y, okay? This is one guarantee that going to be inside the core. Whatever is going to be inside the core, there cannot be a completely different element. There is some similarity. So, so for average, a friendly DP, like what we defined before that, is slightly different. We need, instead of noise R, we need noise 2R, okay? Because of these two F hop that we have here, okay?
What happens if the core is like empty? So
Okay.
as you get like the boundary between sort of non-empty cores and empty cores.
So this is like the reason that we are handling in what we call the insertion deletion model, not changing the point. Like you need to the algorithm after that need to handle an empty core or something that is close to empty. Then usually it will abort or something like that. Okay, you need
right,
that.
But if the algorithm behaves very differently on an empty core from on a core with 1 point, is that going to be a problem?
So a core with 1 point. So again, the algorithm in the next step, what we call the friendly DP algorithm, okay, it must be at least friendly DP. It must handle this case. Okay, it must like even a DP algorithm must handle, like, let's say, check how many points do you have in a private way. If it's too less, then just abort. Okay, you must handle this case. So this tool can give you an empty core, but the next step will abort with high probability.
Thanks.
Okay. Okay, so this is basically the code that we use for DP, and basically this is like the most naive thing. We just use the most trivial probability, which is just take the count. It will be 2c over n minus 1. Okay, just what makes it to be between 0 and 1 in a smooth way with equal jumps. And so the utility here again is that if all the elements like each other, what we call F complete, then the friendly core will be just D. And the privacy is that if A is F friendly epsilon delta DP, which means only private when the databases are F friendly, then applying A on the friendly core is a standard 2 epsilon 2 delta DP. Okay. We started with something epsilon delta. We lost the factor of 2 or something close to that in the privacy, but we are getting a standard DP, not a friendly one. And for zCDP, we have a slightly different construction. So Here we have also parameters rho and delta in the FriendlyCore. And the QC is not explicitly defined. It's just induced by the following process. For every such count, we compute a noisy version of the count. And then we add to see if this noisy version is sufficiently larger than n over 2. Okay, and here the utility, we need to assume that n is at least something. And if this is the case, then we are getting the core with a high probability. A FriendlyCore D will be exactly D with high probability. And the privacy is that if we have an algorithm A, which is a friendly rho 1, delta 1, zCDP, then applying A on the FriendlyCore with rho 2, delta 2, the parameter here, will give us the sum of the parameters. Okay. So just a comparison between the two, what is better, the DP or the zCDP. So the DP is optimal up to a constant. Okay, we only lose a factor of 2. If you don't care about constants, it's great. But zCDP, basically it has an advantage in practice. So when n is large, we can basically set this rho 1 to be most of the privacy budget. Okay, we can only give this FriendlyCore only, let's say, 0.1 of the privacy. We don't have to lose, let's say, factor of 2 like in this case. And also zCDP has the advantage that averaging the Gaussian mechanism is really tailored for zCDP. So for the applications that we are interested, like averaging and also clustering, friendly DP algorithm in the zCDP model are very accurate. Okay, so in this sense, this preferable model. Okay, I'm just mentioning that basically we can also extend this tool a little bit to also allow outliers. So the only difference is that this Q of C needs to be not just one when C equals n. It will be 1 when C is at least n minus outliers. So and then we are going to guarantee that if the point X likes at least let's say 0.9 n of the point, or the other point, it will be inside the core. Okay, as long as there is enough gap between the two here, then this also works. Okay, so let's see an illustration of a mean estimation. So here we have 1,000 samples, 90% from a Gaussian with a small sigma, 5% with a Gaussian with larger sigma. And so basically what we are doing is we are doing a completely different private search for an R using a binary search over this segment, where we are getting that a good R will be 9.85. And then what we are doing is that we are just applying FriendlyCore with this predicate. So this FriendlyCore gives us this point, all these points, which is without almost without all the outliers. And so probably this is like the radius here, it will be okay. And then just do the private average with 2 times this 9.85, and we will get the average. And for clustering, okay, so let's see the clustering demo. So here we have 20,000 points, 90% from low variance Gaussians and 10% from higher variance Gaussians. So what we are doing here is that we random partition to 300 parts, and on each part we run Python k-means, and we get from each execution we get 3 centers. So basically this is the picture of all the centers that we get. This is all the 900 points of all these 300 tuples. And now we apply FriendlyCore on this set of tuples with the predicate that we defined before. And basically it removes some of them. And this is like the picture after it removes the tuples. We get a nicer tuples. it will be 207 tuples out of this 300. And then we are doing the process that we talked about. We pick an arbitrary tuple like the black one. We use this tuple to split into 3 clusters, into different colors. Again, this is safe only because the core is certified to be friendly. You know, it's certified, so this step is safe. And then we compute a DP average of each of the sets to get the red points. And each average also was done using the FriendlyCore for average that we saw. And we get 3 private points. And these are the points in the original data set. And at the end, we are performing to get more accuracy. We are performing a final private Lloyd step with the rest of the privacy budget. Okay, Lloyd steps just mean that I'm splitting the points according to this tuple, and then I'm doing the average in each set. But now I'm taking advantage of the fact that I have a lot of points, so I'm getting an accurate result. Okay, so regarding averaging, so previous results, so there are many previous results about averaging. I probably missed some of them. And basically, most of I don't know if all of them, but most of them at least are tailored for RD. And like our approach, all of these results clip or trim the outliers and then average. But the issue is that this process of clipping and trimming all the other results, basically they are dimension dependent. Okay, when you increase the dimension, the process is going to react in a different way. Okay, it might not perform well when the dimension is too large. But in our case, okay, the process is no dependence in the dimensions. There was no dimension in the process of removing the outliers. So there is, what I'm saying, there is in all the results, there is a dependence in D, because eventually you need to apply the Gaussian mechanism and you will get a noise that is proportional to square root of D. You cannot avoid it. But what I'm saying is that the process of removing the outliers, in our case at least, is not dependent on the dimension. And also our tool is simple and general, not tied to RD or averaging. And as we see next, it's also practical. So we compared our result with the nice result, very nice result of Viswas et al., what we call a coin press algorithm. And so the setting that we are testing is that we have n samples from a standard spherical Gaussian with unknown mean. And the goal is to privately estimate the average of the samples. So what we're seeing now is, so the green one is FriendlyCore, and the other colors is coin press with different iterations. So coin press is an iterative process. They're doing a lot of Gaussian mechanism in iterative process. So we tried a lot of different iterations. And the y-axis is the L2 error from the actual average. And here we are increasing the dimension. The number of points that we are sampled is 800, and there is also a parameter R that we need, because a coin press needs a parameter R assumed bound on the mu, on the mean. FriendlyCore does not need this parameter. So as you can see, when the dimension is large, it doesn't matter basically how much iteration that you take. This is the 2 iteration, the 4 iteration, the 8. When the dimension is sufficiently large, then basically FriendlyCore enjoys the fact that the problem is that it really has an inherent dependence in the dimension in the process of detecting the outliers in the coin press. So when the dimension is large, FriendlyCore is preferable. And also when we increase R, so it's clear that FriendlyCore is independent of this parameter, but also it doesn't matter. So it's not like you might hope that if you, for every R, there is a number of iterations that you can get good results, but this is not the case. There is really a limit. Like in this set of parameters, if I will take R somewhere here, no matter how much iteration we take to compress, it will be give us inaccurate results. But what I say, but it's worth mentioning is that in the low D, low R regime, So I also added here KV, the algorithm of Karva and Vadan. So in this regime, basically CoinPress is slightly better than FriendlyCore. And for the reason, so why CoinPress is better in this regime is exactly because of the factor 2 that we are paying in our friendly definition. So we must pay 2R and not R. So if we could improve this constant, that would be great. But this factor 2 is exactly makes the difference in those cases. Regarding clustering, so there are many theoretical results with no implementation. But recently, Chan and Kamath from Google implemented a very nice work about private clustering based on the local sensitivity hashing in the epsilon delta DP model. So next we're going to see FriendlyCore clustering, okay, where versus this LSH clustering. So in FriendlyCore, again, FriendlyCore might fail. So what we are doing here, we are only getting 0.99 of the row to FriendlyCore, and in case we are in case of a failure, we are just executing their algorithm with the rest of the privacy budget in order to output something. And so why did I choose the epsilon 2? It's just a choice of parameter that none of the guarantees implies the other. Okay, because I don't know really how to compare such models. This is the first experiment. We have n samples from a 2-dimensional 8 separated Gaussians, n over 2 from each Gaussian. And the goal here is to output centers that minimize the k-means cost. So to minimize this, the sum of the square distances of each point to its nearest center. So what we are seeing here is that basically this graph is, we are measuring the normalized k-mean loss, where normalized k-mean loss is the 1 minus the optimum over the cost of the solution. We are increasing n in this case, and the points are so we ran for each such column, we ran actually 30 executions, and the points are the medians of the executions, and the segments are the 10% and 90% quantiles. So here FriendlyCore is, we create 200 tuples using Python k-means. So what we can see that when n is increasing, then basically we are taking advantage. We are getting a very, very accurate result with a very accurate result. Here we basically, FriendlyCore fails in this regime, and therefore we are just seeing what happens with the LSH clustering with the small budget. So when n increases, so FriendlyCore is accurate, while LSH remains somewhat inaccurate. And this is like an example of one of the execution in 200,000 samples. So here the green points are the points of FriendlyCore, and the red ones are of the LSH clustering. In a different experiment, we took 250,000 samples from a mixture of 5 standard spherical Gaussians with separation square root of 2D, which is actually not such separated. They are quite close Gaussians. And the goal is to determine which samples belong to which Gaussian. So here, what we did, we applied FriendlyCore using a non-private algorithm that uses a PCA-based clustering that basically can, with large dimension, can easily separate between such Gaussians. So when the dimension increases, we're taking advantage of this PCA clustering and getting a very accurate results, while LSH remains almost oblivious to this increasing in D.
So, Eliad, what what is the output of the algorithm in this case? It's a classifier.
It's a, yes, it's again, it's like in the k, it's k centers. And just now instead of checking what is the k-means cost, I'm just checking what, I'm taking the k centers, and I'm partitioning into sets, like each point to its nearest center. And then in this case, I just went over all the permutation to see if there is a match to the real labeling of the points.
I see. Okay, so the y-axis here is like the fraction of correctly labeled, incorrectly labeled.
Yes, you take like the best permutation and you see what is the error in the best permutation.
So it's like the, if you think of it as a classification task, which I guess is the way you're thinking of it, this is like the empirical misclassification cost. Right, up to this possible relabeling of the K outputs, right?
Yes, I'm not sure that I understand, but I think that it's like the most, yes, it's a class. The centers are basically classifiers, yes, in this sense. They are classified and just.
I got it. Yeah, thanks.
Okay, and so in the last experiment, we just we checked what happened on real data. So basically, FriendlyCore has it needs some stability. Okay, it needs some stability in order for the tuples to be similar. Otherwise, we don't get anything. FriendlyCore fails. And so what I'm going to show is that such stability can also be we can get from real data as long as we have a lot of data. Okay. So we took a clustering for a publicly available large data set that contains like something like 8 million records of 16 chemical gas sensors over time. So each such record, it's treated like a 16-dimensional point. And as again, the goal is to minimize here the k-means cost. And what we showed is because we have large data, we basically achieve the stability, even that we don't have really a structure. Okay, there is stability of the non-private algorithm, so we are getting very accurate results for k equals 2, k equals 3, 4, 6, and in 5, actually we are failing because basically it's interesting, but here in 5, it seems that there are two different solutions that some of the non-private algorithms gives the one and the other gives the other, and then we don't get similarity between all the tuples and we fail. Okay, and basically what we see is.
Question, did you compare it to just like a noisy version of Lloyd's algorithm?
So the question, what is the noisy version of Lloyd? What the main question, what is the initial sentence that we will start with? Okay, like in Lloyd, you pick, let's say, one of the, you pick k points or something like that, and then you start. So the question, how do you pick the k points? This is like the main question.
Right, so I guess you have a region for the data. Otherwise, like if you have some region where the data lies, otherwise that you couldn't do the final step of Lloyd's algorithm that you talked about, right?
Yeah, so this is like, I think that you can, I think that somehow maybe the LSH is something similar in a more sophisticated way doing something like that. It's somewhat split, try to find a good place to put the centers using this LSH, but otherwise you need some way to do it. This is the issue, that the initialization is the issue in the cluster.
I see. So it's like random initialization or something like that ends up not working well.
So yeah, maybe you start with random initialization, maybe you'll do a lot of Lloyd steps. I don't know. This is something that also, it's nice to see what's happened. So we only compared with the LSH, we didn't try to implement such a...
My experience is only with very low dimensional versions of this that I've given as student exercises in classes. But with like 2- and 3-dimensional stuff, random initialization seems to work pretty well. But
yes.
Yeah,
So
I mean, I realize it behaves very differently in high dimensions, but it's like the fact that you need n to be so large because of the sample and aggregate step.
Yeah.
That suggests that, there might be room for improvement.
Yeah, I'm not saying so. The bottom line, I'm not saying that our algorithm is like the best one. What I'm just saying, our algorithm, in case there is stability, we are getting a very accurate result. In many cases, we are getting because you really gives like the non-private algorithm. Okay, you are really giving what non-private algorithm gives, and in that cases, we are giving a very accurate result. In other cases, we fail, and then maybe Lloyd and other things, and LSA and other algorithms are better. Okay, it's not just. I'm not saying that this algorithm is like the best algorithm that you always need to use. It has the disadvantages.
Thanks.
Okay. So for summary,
I have a stupid question. I think I may have missed something on the previous slide. So like for k equals 4 and k equals 6, like you're getting like really good accuracy, but like why is like k equals 5 kind of an anomaly here?
So again, what happened in this case is that it seems that there is two solutions that are, each of them gives a good 5 means solution, but they are different, okay, different centers. And so when you split into 200 tuples, then some part of them, the non-private, find the one solution, and the other tuples are the other solution. And then you don't get, so in order to FriendlyCore to succeed, you need that all the tuples to be similar or close to all the tuples, okay? And when you have half this and half that, FriendlyCore fails.
I see. Sorry. Yeah, thank you.
Okay. So for summary, FriendlyCore is a tool for private aggregation, and we saw an example, averaging and clustering, and it can also support further applications. So for averaging, we saw the advantage on high dimension, and also it's not tailored for Gaussians. We can give a utility guarantee not related to Gaussian points from a Gaussian distribution. And for clustering, so FriendlyCore gives us an accurate result on success, a very accurate result on success, but it might fail. So it seems that FriendlyCore plus LSH or maybe Lloyd step or something like that as backup can be preferable in many cases that we are thinking that we might have a good stability of a non-private algorithm. And that's it. Thank you. If you have any questions.
So I had maybe one question, but another question, but I wanted to allow others to ask questions. Can you tell us about the privacy analysis of the sort of the pruning step where you remove unfriendly points or unpopular points?
So again, regarding the analysis, so what I didn't told you, so
you had a theorem somewhere that listed
yes.
the privacy.
Let's see. So here, for example, maybe let's start with the DP. With the DP, basically what we are guaranteeing is that the course, the C and the, so the friendliness is guaranteed by definition here, okay? Because points with no more than n/2 are not inside the core. So what I just need to show you is that somehow the cores are similar. And basically what you are getting here is the cores up to the additional points has, if you look at all the probabilities, then the L1 norm of them is small, is maybe 1 here, I'm not sure, 1 or 2, I think 1. And means that the statistical distance is small. So there is a claim to say that if you are studying with 2 databases that have L1 norm, 2 of them are random with probabilities that are close to each other, then when you are applying a DP algorithm on this to execution, it will be then you are getting to lose this factor. Okay, somehow the norm comes into this equation. So this is like the analysis in the DP. We need to translate random databases of small L1 norm, what's happening when you give it to a private algorithm. And in the zCDP, basically what we're getting a stronger guarantee on the cores in this case, because the core are just a post-processing of this noisy C. Okay, so their cores are really indistinguishable, like indistinguishing privacy. And then, therefore, we are basically getting that the core here, the cores here are row 2, delta 2 indistinguishable, and we have an algorithm for 1, delta 1. So basically, it's some kind of a composition. It's a little bit subtle, but it's not. But mainly, this is basically composition, which shows basically follows from composition.
Sorry, so you're saying the cores themselves are indistinguishable, like
up to the additional points. So you have basically you have two cores.
Up to the additional point. I see that.
Yes, up to the additional points, all the other elements are indistinguishable. So you have two random databases that are close to being neighboring. Like all the other points are similar, and you have one additional point. So you just need to say that if you apply a DP algorithm on such a random databases, so it's like applying so it's like composition. You have the composition of the randomness of the database, and after that the looseness in the algorithm when the database are really neighboring.
And are you saying that that's not true for the previous, the
DP?
DP analysis, the previous
one?
one?
No, it's the same. In the DP analysis, it's the same idea. Again, you have two similar databases with additional point, but in the DP, the similarity is not in DP indistinguishability. The similarity is just in the statistical distance or a small L1 norm. So you need to somehow claim that it doesn't follow from a composition. Okay.
I see. It's like a different kind of composition, right?
Yes. Yeah.
Is there one ish? Well, okay, I don't want to call it an issue, but one aspect of this algorithm is that it really looks at the sort of pairwise notion of friendliness, right?
Mm-hmm. Yes.
Which I guess for a lot of high dimensional problems might not quite capture what we think of naturally as outliers, right? So often outliers might be defined by a relative to some global feature of the data set, like a subspace where most of the data points lie or something like that. Right? So have you given any thought to sort of extending this approach to kind of other types of
there is one, so this is actually not our work, but it's an independent work of other guys at Google. I don't remember the names, but basically you can use this approach. They also did something similar using sample aggregate, something similar to that, but not for clustering and other. They did it for estimating the covariance matrices of Gaussians with unknown bound on the norm of the covariance. Okay, so basically you can somehow sample points, and in each such set you estimate the covariance matrix, and you can define some special predicate such that covariance is a friend of other covariance matrix. And then you can use it, like when you have a friendly set of covariance matrices, you can use it in order to define, let's say, a friendly algorithm that can estimate it without any known bound. So many results need some bound on the norm of the covariance, but with such kind of thing, you don't need it.
Sorry, is this paper public? I know there's been 3 simultaneous papers that solved this problem. I'm wondering if there's a 4th one.
Yes, this is public.
Is this the paper by what's it
No,
called?
what I say, this paper or the paper
Yeah,
of the
your
Kubernetes?
paper is public. I know I've seen it online.
Yes,
but
we have yes, our paper has a old version public, and and soon I will add the more updated version.
okay, but I'm curious about this covariance result that doesn't have a dependence on the bound. Do you know if that result is public? Is that
Yes,
part of
it's
your
public.
work?
It's public. Yes, I read it because I know, so it's public.
Okay, is that the paper by Pawson, Amaya, and Pravesh, or is it?
I will just by don't know how to find it now.
Sorry, yeah, I don't mean to put you on the spot. Sorry, yeah, but I'm just wondering, was like, you mentioned, does this use the FriendlyCore paradigm or something else?
It uses a paradigm that is somewhat similar to this. So basically, instead of instead of doing some probabilistic method of what gained is inside the core or out the core, they're doing some weights, deterministic weights that are with like you have a weighted data set, and then the weights are the weight is, let's say, 1 when the element is good, and is 0 when the element is bad. And then in this weight data set, you're doing some average weighting, and then they define an algorithm on such average weighting that should be, I don't know how they called it, but not friendly, but in the sense friendly.
Right. Okay. Yeah. I guess, yeah, I actually read this paper recently, and I guess it's somewhat similar to, I guess, what you're saying. Yeah, they try to assign like 1s for the good points and 0s for the outliers, and
Yes.
yeah, the softer way of doing that. But yeah, okay, I guess I can see the kind of connection. Cool. Thanks.
Yeah. Any more questions?
Okay, let's thank Eliad for the end of this talk.
Thank you.
Okay, just an administrative point. So